Now that we have this concept of limits and how we can evaluate, now let's take a moment and look at the properties of limits and see what all can you do with this. How can you manipulate a limit? How can you do little details? Because these details are going to help us to be successful in our harder concepts when we're able to break off a piece or separate or combine things as we go. So some of our basic properties we want to look at is number one, the limit as x approaches c of b is equal to b. Meaning if we were taking the limit of some constant b, then it's just going to be that constant. And so let's just kind of write an example out to the side. So just an example here. If I have the limit as x approaches 2 of 3, that's just going to be 3. And this makes sense because 3 is just the equation of a horizontal line. And so am I approaching a value on that horizontal line? It's just going to be 3 the entire way. It doesn't really matter what value I'm approaching because horizontal, left and right, it's going to get us there. Number 2, if I have the limit as x approaches c of x, that's going to be equal to c. And that goes back to our basics of just plugging it in. So say I had the limit as x approaches -4 of x. Well, that's just a linear function. So if I straight plug in, I get a value of -4. No big deal. Just some basics to get us going. Number 3, if I have the limit as x approaches c of x to the h, then that would just be c to the h. Similar to number 2, just had that exponent on it. Say I had the limit as x approaches 3 of the function x squared. I could just straight evaluate, say 3 squared, and give me 9. So no big deal. We have a property for limits at constants, limit at a first power, and limit at any given power of an integer there. But some of the special properties that we can get into are going to be these down here, and these are going to help us as we work with more complicated problems in order to break off pieces that we know and then focus on the more complicated set. So the first one is scalar multiplication, and here's what scalar multiplication does for us. If we have a limit, say as x approaches c, of some b being multiplied by f of x, then that would just be equal to, we can pull that scalar b out front of our limit and say b as x approaches c of f of x. And for these properties, what I've done here is just identified a limit of f of x equal to L, and then a limit of g of x equal to k, just being two generic functions and having a limit of L and k, so that as we work through these properties, we can pull things out, put things together, and then you can see how the limits work from there on the other side as well. And so with this one, when we pull that b out front, we can just take the limit of f of x, and we know that to be equal to L, so it ends up being just b times L. So that's really nice. If we have a scalar or some coefficient, we can pull those out front, carry them along for the ride, and then just multiply them by the limit at the end. The second one is sum and difference. So say I had the limit as x approaches c of f of x plus or minus g of x, meaning whether you're adding functions together or subtracting functions, then that's just going to be equal to the limit of f of x, which is L, plus or minus the limit of g of x, which is k. And so you're just going to be adding and subtracting the limits of the individual functions. So again, that's going to make it nice, especially with some more difficult limits. Number 3, product. If you have the limit as x approaches c of f of x times g of x, good news, that is just the limit of f of x times the limit of g of x. So that's really nice too, that multiplication is just the multiplication of those limits. Number 4, quotient. We say that if we have the limit as x approaches c of f of x over g of x, then again, that is going to be the limit of L over k, like you might have predicted based on the other two. And then just, as always, k cannot be 0, something we've been working with. The power property says that if you have the limit as x approaches c of f of x to the n It's just going to be your limit raised to the n power. And then composition, this one can get a little bit tricky. If you have the limit as x approaches c of f composed with g, remember composition of functions, then that's going to be the limit as x approaches c of f of the limit as x approaches c of g of x. So remember with compositions, if you've had me for previous courses, we always teach that the first one is your template, the second is your plugin. So you could compose that function and then take the limit, or an alternate way of dealing with compositions is working from your inside out. So you could go ahead and find your limit of g of x, that value being k, and then plug k into the limit of your f. So the composition one can get a little bit hairy there, but these properties are going to be really nice for us. You're also going to see a replication of these properties in later sections in chapter, and they're going to revisit again in Cal 2. And so having these as a tool in your tool belt is going to be beneficial, especially again in harder concepts and theorems, corollaries, etc. So based off some of these, we can do a lot of things, but it wouldn't be a calculus section if we didn't add in some trig. And so for the next part, what we're going to do is we're going to look at some trig functions and their limits and how they work out. Now, some of these work out really nicely, and some of these we're going to have to pull out a little bit more of our trig knowledge. Hopefully you're bringing that back up from your pre-cal days. When we're looking at trig functions, sometimes you just want to go ahead and try some substitution first. So if you're a little rusty in your trig, we are going to be revisiting that here. So the first one here says, what is the limit as x approaches 0 of tangent x? Well, if we just straight evaluate this, this would be equal to the tangent of 0. Now, if you haven't forgotten, reminder, tangent x is equal to sine x over cosine x. And you should know this. This should not be something we have to keep looking up. And so if I go back into my problem, this would be the same thing as sine of 0 over cosine of 0. And you've already been working with your unit circle earlier in the modules, and so hopefully you're remembering that as well. And so if you go to your unit circle, this would be angle 0. And remember, this ordered pair is 1, 0. And the first one is cosine of 0 at that value, and the second value of that ordered pair is sine at that value. So I know that sine of 0 would be 0, cosine of 0 would be 1, and this reduces to just 0. So you've got to remember that unit circle. There will be no formulas or unit circles given on any exams. So make sure you're fresh on these foundational concepts of knowing tangent and especially your unit circle at that point. Now looking at example number 2, we've got a little bit more going on. So let's approach it the same way. The limit as x approaches pi of x cosine x. So that would be equal to, we're going to straight evaluate, pi of cosine pi. And so then let's consider where that is on a unit circle. So pi would be all the way over here, because remember, your entire unit circle is equal to 2 pi. So the ordered pair that would be over here would be at -1, 0. And again, they're in alphabetical order. This would be cosine of pi. This would be sine of pi. So -1 is what I'm wanting. Oh, I already had an equal sign. And so I have pi from right here. And then cosine pi is equal to -1. So this ends up being -pi. Now I wouldn't want to run to my calculator on that one by any means, because -pi is an exact answer, and I do not want round decimals. I would like exact answers wherever possible. So let's look at this next example now. It says the limit as x approaches 0 of sine x over x. This is going to be equal to sine of 0 over 0, but we can't do that. We can't divide by 0. And so what we're going to do is we're going to learn a new theorem in order to help us to solve this. And what it's going to do is it's going to show us 2 different facts or trig functions that we can actually use to help us. And so let's look at this part here and go ahead and go to the next page. And so it says something known as the squeeze theorem. Now, the squeeze theorem is really pretty neat. It says if you have g of x less than or equal to f of x less than or equal to h of x for all x near but not equal to c, and the limit of g of x is equal to h of x is equal to L, then the x approaches c of f of x is equal to L as well. And so let me slow down and say that again. If you have g of x, this small function, and h of x, this large function, with f of x contained between them, kind of sandwiching them in, and you know that the limit of g of x and the limit of h of x both equal L, so this has a limit of L and this has a limit of L, then they squeeze the middle function to also have a limit of L. And there's a really neat proof that goes along with this, and I'm going to link that in the lecture pages under the resources. But there's two facts that we get from this, and two facts we're going to use quite frequently when working with our trig functions. We get this first fact of the limit as x approaches 0 of sine x over x is equal to 1. You can see by straight evaluation that did not work out for us. And the proof of this function, again, it's in the resources, is really pretty neat. It takes your unit circle and 3 different triangles and shows you how the area of those triangles, how they converge together, and it takes limits. And so definitely check that out. Little 4-minute video, but it's really neat on how that one works. Now, we're not going to prove that every time. We're not going to take that long process. I mean, we got things to do. And so we're going to take this number 1 as a fact, that the limit as x approaches 0 of sine x over x is equal to 1 is a fact, that is equal to 1. We're going to use that fact, or sometimes these are theorems stated in your text, and use it to manipulate other trig functions and other trig limits in order to work out a little bit better for us. The other fact that we get from that is this one here, and it's dealing with cosine. And it says that the limit as x approaches 0 of 1 minus cosine x over x is equal to 0. And again, there's a proof for that, but we take these as theorems or facts that we can then use and manipulate in other situations. So let's take a look at some of those examples. Previous examples, we were able to evaluate. These, we're going to have to do a little bit more work. So we're going to do some little algebra manipulation. You might be cringing about every time I say algebra now, seeing how much we use it. But it says the limit as x approaches 0 of sine of 4x over x. Now, something that is interesting is that you'll notice sine of x over x have the exact same function that we are taking the sine of. But if you look in our problem, we have 4x and x, and these are not the same. So in order for me to use this fact or theorem, I'm going to have to manipulate my example to resemble that. And so what I'm going to do is I noticed that if this were also a 4x, that I could use that fact. So in order for this to be equal and not change the value of the equation, I'm going to have to also put a 4 on top, because 4 over 4 is just 1. It doesn't change the value. So this is going to be equal to the limit as x approaches 0 of 4 sine 4x over 4x. Now we learn from our properties that we can move scalars out front, and so then that would give me equal to 4 times the limit as x approaches 0 of sine 4x over 4x. And then that right there is use of that fact that we already have, which we know to be equal to 1. So it gives me 4 times 1, which is just 4. So pretty neat right there. And showing something like that, these would be the steps that you would need to show in an exam situation, not just go, oh, I know it's going to work out to be 4. You got to show your use of your theorem and your steps to getting there. Now let's look at the next one. It doesn't look clearly that we're going to use these theorems, but I do have tangents, so let's do a little bit of manipulation. And so we already saw previously that we had to pull up some pre-cal knowledge, and we said, you know what, when we have tangent x, that is equal to sine x over cosine x. So we're going to have to apply that here with this tangent x. And so what I'm going to do is I'm going to go ahead and kind of change that around, and that's going to be equal to the limit as x approaches 0. Now instead of tangent, I'm going to do sine over cosine. So that gives me sine x over cosine x. Now I can't forget this little x, so I'm going to just place it here in the denominator. Then if I take that fraction apart, kind of unmultiply it, that would give me, I'm going to separate out the sine x over x, this piece here, into one fraction, times 1 over cosine x. Just kind of unsimplifying it. Well, again, that works out really nicely for me because we know this limit here, and so I can separate those two out. And so then that's going to give me equal to the limit as x approaches 0 of sine x over x times the limit, again basic properties here, of x approaches 0 of 1 over cosine x. Now this is the part that we just pulled up from earlier, and so we already know what this is equal to. And this is equal to 1. The limit as x approaches 0 of 1 over cosine x, we can actually work by evaluating. So that gives me cosine of 0. So it gives me 1 times 1 over cosine of 0 is just 1, and 1 times 1 gives me 1. So pretty neat right there. Just manipulating that tangent, we were able to see that we had that sine x over x emergent, and then we're able to work it out from there. Let's do another one, and let's use this one that we have outlined in blue and see how that's going to work out for us. Now with this one, let me fix a little error here. This should be as x goes to 0. Okay, so if you look at this one, you can see that we have this 1 minus cosine x going on here. And what we can do is we can use that property of scalar multiplication, and we can actually bring this 4 out front. So that gives me 4 times the limit as x approaches 0 of 1 minus cosine x over x. And again, we know this to be a fact that we have. And so that's going to be equal to 4 times 0, which just gives me 4. And so you can see the usefulness of using that squeeze theorem and the facts that come out from it. Now, a couple more things we want to do to kind of end this lecture, and we're almost done here, is let's kind of remember a function. We don't use it super often, but we do need to address it if we're talking about limits and all the different functions we're going to encounter. And this is called the greatest integer function. And how we understand this, it's really kind of interesting. It really turns out to be the least integer function, or a step function. And so the way it is written is it's f of x equal to kind of a double bracket of x. If you're handwriting it, typically you can kind of do a bracket with an extra stem on it of x, something like that. And it's the integer of x. And so what we want to do is, let me just kind of number our graph here so we can find some values. Is when we're looking at this, we are going to, if it's not an integer when you're evaluating it, you round down. So that's kind of a Zobchik thing there, round down. So when you're looking at this, you look at f of 1. Well, if I were to plug 1 into this function, 1 is an integer, and it would just output 1. And you can see I have a value of 1 there. Now if I look at f of 1.2, well, that would be double bracket of 1.2. Is 1.2 an integer? No. So round down. So if you round down 1.2, it just gives you 1. Graphically, you can see 1.2 would be about here, and it would also have a value of 1. Now it's those negative decimals that normally get students, negative 1.5. So that would mean when you plug it in, you get negative 1.5 in that double bracket. And you say, is that an integer? No. So round down to the least integer, or the greatest integer less than or equal to. That's why they call it a greatest integer function. And the greatest integer less than or equal to it would actually be negative 2. So let's take a look at that. Here would be negative 1.5. And at negative 1.5, it is at a value of negative 2. Because it is the greatest integer less than or equal to, really the least integer function. Or my favorite way to say it is round down if it's not an integer. Now, that's pretty basic. That's kind of an algebra thing. Let's look at what that's going to happen when we look at our limits at those. And so just kind of another shorthand is to do this capital INT here. And so when I go to plug in 8.6, just remember how to do this. So this would be, I'm either going to use this notation or I can do the double brackets. And so this would be INT of 8.6 plus 2. Just like with anything, follow your order of operations. And so I'm going to do my parentheses first. So int, that would give me 10.6. Now 10.6, you want the greatest integer less than or equal to it, or I like to say round down. And so then that would actually give you 10. And so make sure you kind of remember how to work with this function so that the limit doesn't trip you up. Now, one last thing that I want to reiterate for this section is I want to look at the slope of the tangent lines and using limits, because we spent all of 1.0 looking at tangents and secants, and so there's something really interesting that's going to happen here and a very important concept, and the whole reason we have this short little chapter going on here. If I take my function, this is going back to 1.0, let me just kind of rough draw. There's that quadratic we were looking at in section 1.0. And so say I'm looking at this point here, and this is x. So this would be f of x of that function. And we talked about how if we take 2 points, so let me pick this point here, and this would be at x plus h away. We talked about how if we took 2 points and had a secant line and move them closer and closer. So this would be f of x plus h. And we can see that this point is just h units away. Well, if I take the slope, hang with me, the reason I'm jumping back to 1.0. If I take the slope of that secant, and we talked about how that's f of x plus h minus f of x all over x plus h minus x. And then if I simplify that, so let's see, my x's are going to cancel. So that gives me the slope of that secant would be equal to f of x plus h minus f of x all over h. If I take this h and I make it smaller and smaller and smaller and closer and closer and closer till I get to that tangent, remember we talked about this, this would be the slope of the tangent would be equal to the limit as h approaches 0, getting closer and closer, of f of x plus h minus f of x all over h. The limit of that is going to be my slope of my tangent. And so here we are at 1.2, we're putting it all together starting from 1.0 to here. And so we're back to that original situation of how do I find slope at a tangent so I can create not just a secant but a tangent at this point. And we're going to use that by that limit process of decreasing the length of h that we are taking. Now this is super important, and so very important. We're going to work with this. We're going to work with this functions. You're going to be so tired of it when we get done with it. So I think that's a good stopping point for here, this section. So if you have any additional questions in 1.2 or need some additional resources, please reach out to me through Canvas messaging.